Okay, let's start with the basics. What is Asterisk Data Science? It's really a fascinating blend of different skills and approaches. Basically, we use scientific methods to dig through all this information, whether it's from databases, websites, or even sensors, to find valuable insights. We clean up that data, which can be messy, and then we explore it to see what patterns are hiding within. Finally, we build models and algorithms to make predictions and automate some really smart decisions. It's all about transforming raw information into something truly useful. Okay, so when we talk about data scientists, it's really important to understand they do much more than just write code. They start by gathering all the data. Think of it like collecting ingredients for a recipe. Then they need to clean that data, making sure everything's accurate and consistent. Next up, they dive in with exploratory data analysis, which is basically getting to know their data really well through charts and graphs. A big part of their job is feature engineering, creating new helpful elements from the existing ones to boost model performance. After that, it's time to build models using things like regression or classification to solve real-world problems. But it doesn't stop there. Data scientists need to be able to explain what they found in a way everyone can understand, so they have to be good communicators and tell a story with the data. Okay, let's get clear on the differences between data science, data analytics, and data engineering. Data analytics is all about digging into past data to answer specific questions like what happened last quarter. Analysts use tools like SQL and Tableau to find insights. Then we have data science, which goes a step further, using that information to predict what will happen next. Data scientists build models and algorithms to make those predictions, often using Python or R. And finally, there's data engineering. These folks are responsible for the entire data ecosystem. They design and maintain the systems that collect, store, and process all of this data, making sure it's available when needed. Okay, let's talk about CRISP-DM. It's like a roadmap for data science projects. It breaks down the whole process into 5 clear steps. First, we start with business understanding, figuring out exactly what you're trying to achieve and who needs to be involved. Next, we dive into data understanding, looking at your data sources and making sure it's clean and useful. Then comes data preparation. This is where all the messy work happens, cleaning, transforming, and getting the data ready for modeling. After that, we move on to modeling, choosing the right algorithms to build our predictive models. Finally, we evaluation, assessing whether the model truly solves the business problem before putting it into action. Okay, so let's talk about getting started as a data scientist, specifically how we frame the problems we're tackling. It's really important to start with a crystal clear understanding of what you're trying to achieve. Don't just jump into collecting data. Instead, clearly define the business problem you're aiming to solve. Then figure out what data is needed to actually address that problem. Next, we create hypotheses, essentially educated guesses about potential solutions or relationships within the data. These need to be testable. Finally, we choose metrics to measure our success and rigorously analyze the results of our experiments. Okay, let's talk about where we actually get our data. As a data scientist, you'll be dealing with lots of different places information comes from. There are tons of options out there, things like government websites that release public datasets, or platforms like Kaggle which have loads of pre-cleaned data just waiting to be used. Then there's API. Think of them as special doorways that let you grab specific information directly from services like social media or financial markets. Web scraping is another option, where you extract data yourself from websites, but always do it ethically. Finally, many companies store the data in databases, structured ones like SQL and more flexible ones like NoSQL. And don't forget about sensor data, things like weather stations that constantly send information our way. It's really important to think carefully about the quality of your source material too. Make sure you know where it came from and how reliable it is. Okay, let's talk about the different types of data we work with as data scientists. We often hear about structured, semi-structured, and unstructured data, and it's important to understand what each means. Structured data is like a perfectly organized spreadsheet. Everything has its place, making it easy to search for and analyze using tools like SQL. Then there's semi-structured data, which isn't quite as rigid but still uses tags or markers to give us some context. Think of JSON files or XML documents. Finally, we have unstructured data. This is the Wild West. It doesn't have a set format at all. Things like emails, images, and audio. It requires more sophisticated techniques to make sense of. Okay, so let's talk about cleaning and prepping data. It's a really important step before you can actually start building models. Think of it like tidying up your room before you want to put anything away. We deal with missing values, which are just gaps in the data. There are different ways to handle those. You could replace them with averages or medians, or sometimes, if they're too numerous, you might just remove rows with missing information. Then we look for outliers. These are points that seem really far away from the rest of the data. Sometimes they're errors, and sometimes they represent something interesting, but you need to investigate them. We use techniques like box plots and z-scores to spot them. Finally, we often need to transform our data, scaling it so all the features are on a similar scale, and encoding categorical variables so that computers can understand them. Okay, let's talk about a really important part of being a data scientist, dealing with missing data. It's surprisingly common to find gaps in datasets. Think errors in surveys, or just situations where information isn't available. Ignoring these gaps can seriously mess up your models and give you misleading results. There are a few ways we can tackle this. One option is simply removing rows or columns that have lots of missing values, but be careful with this, as you could lose valuable data. Another approach is imputation, basically replacing those missing values with estimates. We could use the average value for a column, the median, or even predict them based on other information we have. Techniques like k-nearest neighbors can also be really helpful here. Ultimately, the best strategy depends on what kind of data you're working with and how it might impact your analysis. Okay, let's talk about outliers, those data points that stick out like a sore thumb. They can throw off your analysis and make it seem like there's something wrong with the rest of your data. There are several ways to spot them. We can use statistical methods like z-scores or the AQR, which helps us identify values far away from the typical range. Clustering algorithms, specifically dbScan, can also pinpoint outliers that aren't part of any established group. And then there's isolation forest, a technique that builds decision trees and isolates these unusual points. Once you found them, what do? You have options like removing them if they're clearly errors, but be careful. Transforming the data with things like log transformations or winsorization can also help. Or, sometimes, it makes sense to simply replace those outliers with more reasonable values using methods like mean imputation. Okay, let's talk about exploratory data analysis, or ADA. Think of it as data detective work. Your mission is to get really familiar with the dataset you're working with. EDA is all about understanding what your data looks like at first glance. We'll be looking for things like missing information, unusual values, and how different variables relate to each other. We'll start by cleaning up any inconsistencies, then dive into examining each variable on its own, and finally, see how they might interact with one another. Let's talk about how we turn numbers into stories. Data visualization is a really important part of being a data scientist. It's all about taking that raw data and making it easy for everyone, not just you, to understand what's going on. There are a bunch of different techniques, like scatter plots, which help us spot relationships between two things, bar charts for comparing categories, line graphs if we're tracking something over time, histograms to see how spread out our numbers are, and box plots to quickly highlight any unusual data points. The key is to choose the right tool for the job. It really depends on what you're trying to show. Let's talk about how we actually show our data. As a data scientist, you'll be spending a lot of time visualizing your findings, and it's important to choose the right tool for the job. Matplotlib is a really solid starting point. It gives you total control over every aspect of your plots. Seaborn builds on that, making it super easy to create beautiful statistical visualizations. Then there's Plotly, which lets you make interactive charts that people can explore themselves, perfect for dashboards. And finally, we have Tableau and Power BI. These are powerful business intelligence tools designed specifically for sharing data insights with a broader audience, often without needing any coding at all. Okay, let's talk about the statistical building blocks for becoming a data scientist. At its core, data science is all about uncovering insights from information, and statistics provides us with those tools. We'll start with descriptive statistics, things like the average, median, and standard deviation. These help us summarize what our data looks like. Then we delve into probability to understand how likely certain events are. We also need to know about hypothesis testing. Essentially, it's a way of checking if our observations align with what we think is true about a larger group. Finally, regression analysis lets us model relationships between different variables, really powerful stuff for predicting outcomes. Don't worry if some of this feels tricky at first. Remember, statistics are just tools to help you understand your data better. Okay, so when we're dealing with data, it's important to both understand what's asterisk the data itself and what that data tells us about the bigger picture. Descriptive statistics are like creating a detailed report. We calculate things like averages, how spread out the numbers are, and even if they're skewed. Then inferential statistics comes in. It's all about using a smaller piece of information, a sample, really to make educated guesses about a larger group or population. We use hypothesis testing to see if differences between groups are real, confidence intervals to give us a range where the true value likely is, and regression analysis to uncover how different factors relate to each other. Okay, let's talk about probability and distributions. They are absolutely crucial for any data scientist. Basically, probability tells us how likely something is to happen. Think of it as a number between 0 and 1, where 0 means it definitely won't happen, and 1 means it's guaranteed to happen. We also have random variables. These are things that change randomly, like the roll of a die or the height of a person. Then we dive into distributions. These are families of probability distributions that help us understand patterns in data. We've got discrete ones, which deal with countable things like coin flips, and continuous ones, like heights or temperatures. There are some really common ones: Bernoulli for simple success/failure, binomial for the number of successes in a series of trials, normal, which is incredibly widespread, and Poisson for counting events over time. Okay, let's talk about two really important ideas: the central limit theorem and the law of large numbers. The CLT is basically saying that if you take a bunch of samples from any population, no matter how weird its original distribution is, the average of those samples will start to look like a nice, normal curve. This lets us make educated guesses about the whole population just by looking at the averages of our samples. Then we have the law of large numbers. It tells us that as we gather more and more data, the average of all that data will get closer and closer to what we'd expect the true value. These two principles are absolutely fundamental to how a lot of our statistical analysis works in data science, so it's worth really understanding them. Okay, so let's talk about hypothesis testing. It's a really important tool for data scientists. Basically, we use these tests to see if the things we think are true about our data actually hold up under scrutiny. We have three main players here: the t-test, which is all about comparing means between two groups; the chi-square test, which looks at relationships between categories; and ANOVA, which helps us compare more than just two groups. Each of these tests has its own rules. You need to understand those rules to use them correctly. Don't hesitate to ask if anything's unclear. Okay, let's talk about a really important concept in data science: correlation versus causation. Correlation just means that two things tend to move together. If one goes up, the other often does too. Think of height and shoe size, they're correlated. But correlation doesn't equal causation. Causation is when one thing actually causes another. It's a cause and effect relationship. It's super easy to mistake them for each other, and that can lead to really bad decisions if you don't understand the difference. So, always ask yourself, is this just a coincidence, or is there a genuine connection? Okay, let's talk about linear regression. It's a really common technique used by data scientists to predict things. Think of it like drawing a line that best fits a set of points you're trying to find a straight line relationship between two variables. The equation is super simple. Y equals mx plus b, where y is what we want to predict, x are our inputs, m is the slope, and b is the intercept. It's used all the time, for example, predicting house prices based on how big a house is. It helps us understand trends and make informed predictions about future data. Okay, let's talk about logistic regression. It's a really important tool for data scientists. Basically, it helps us predict whether something will happen or not. Think of things like predicting if a customer is likely to leave a company or if a loan application is likely to be fraudulent. It works by creating a mathematical formula that combines our input features and then uses a special curve called the sigmoid function to give us a probability between 0 and 1, essentially how likely it is that something will happen. Okay, let's talk about decision trees and how they fit into the world of data science. Decision trees are like a flowchart. You keep asking questions based on your data to eventually arrive at a prediction. They're really easy to understand, but can sometimes get too complex and start making mistakes if you don't watch out. Now, random forests take this concept further. Think of it as a whole team of decision trees working together. Each tree looks at the data in a slightly different way, and then they all vote on the best answer. This usually leads to much more accurate predictions than a single decision tree by itself. Let's talk about support vector machines, or SVMs. They are a really cool technique in machine learning used primarily for classifying data. Think of things like spam detection or image recognition. Basically, they try to draw the best possible line or plane to separate different groups of data. The key idea is maximizing the margin, which is the space between that line and the closest points from each group. SVM are particularly useful when you have a lot of features in your data, or when there aren't simple, straight lines separating those features. They can also use different kernels to handle complex relationships between the data. Let's talk about k-nearest neighbors, or KNN. It's a really intuitive algorithm that helps us predict things by looking at similar data points. Basically, imagine you have a new piece of information and you want to know what it is. KNN finds the k most similar examples from your existing dataset and uses those to make a prediction. It's surprisingly straightforward, but it can be quite powerful, especially for simple classification problems. We'll look at how it works step by step, considering things like choosing k, calculating distances, and finding those nearest neighbors. And of course, we'll also discuss some of its strengths and weaknesses, like how easy it is to implement but can get slow with massive datasets. Okay, let's talk about naive Bayes. It's a really cool algorithm used for classification, basically figuring out what category something belongs to. The core idea is based on Bayes' theorem, and it makes a rather bold assumption that all the features we use are independent of each other. Don't worry too much about the technical details right now. The important thing is that it's surprisingly effective, especially for things like classifying emails as spam or determining what topic a news article is about. It works by calculating probabilities how likely something is given certain features, and then uses Bayes' theorem to refine those probabilities based on what we actually observe. Okay, so let's talk about ensemble methods. These are techniques that use multiple models working together to make better predictions than any single model could on its own. We start with bagging, where we create several versions of our initial model using different chunks of the data and then average their results to smooth out the predictions. Next up is boosting. This method builds models one after another, each trying to fix the errors made by the previous ones. Finally, stacking takes all these individual models' outputs and uses a meta-learner. Think of it as a master judge to combine them into a final prediction. Okay, let's talk about gradient boosting. It's really a fantastic way to build incredibly accurate prediction models. Basically, it works by adding weak learners. Think of them as little experts one at a time. Each new learner tries to fix the mistakes made by the previous ones, gradually improving the overall prediction. We're going to look at three main players, XGBoost, LightGBM, and CatBoost. Each has its own strengths and weaknesses, so understanding those differences is key. XGBoost is super optimized and handles missing data really well, but you have to be careful about overfitting. LightGBM is great for huge datasets because it's fast and efficient with memory. CatBoost shines when dealing with categorical features. It can handle them directly without needing a lot of extra work. It's a powerful technique, especially when paired with good data preparation. Okay, let's talk about picking the right model and then figuring out how good it is. It's not always obvious which model to use. It really depends on what you're trying to predict or classify, and of course, the data itself. We have options like linear regression for simple relationships, logistic regression for things like spam detection, decision trees and random forests that are pretty versatile, SVM for complex data, and then neural networks when we need something really powerful. Once you've chosen a model, you need to evaluate it. There are different metrics depending on whether you're predicting a number regression or classifying things like good vs bad. R-squared and MSE tell us how well the model fits a regression problem, while accuracy, precision, recall, and phone score give us a picture of how well our classification model is doing. It's really important to look at several metrics together because no single metric tells the whole story. What matters most depends on your specific goals. Okay, let's talk about how we measure how good our models are at predicting things and classification problems. Accuracy is the simplest, just the percentage of correct guesses overall. But if one class is much more common than another, accuracy can be misleading. Then you have precision, which tells us out of all the times we said something was positive, how often it actually was positive. And recall, which asks, out of all the things that were truly positive, how many did we catch? Phone score is a clever way to balance these two. It's like finding a sweet spot. Finally, ROC-AUC is a really useful curve that shows us how well our model separates classes at different thresholds. Okay, let's talk about how we measure whether our regression models are doing a good job. We've got several key metrics to consider. First up is MAE, it's the mean absolute error, which calculates the average of the differences between our predictions and the actual values. It's super easy to understand because it gives us the average prediction error in the same units as the thing we're trying to predict. Next, we have MSE mean squared error. This one penalizes bigger mistakes more heavily, so it's good for spotting outliers. Then comes our MSE, which is just the square root of MSE. It's in the same units as our target variable, making it easier to interpret. Finally, there's R squared, or R2, which tells us how much of the variation in the data our model can explain, basically how well it fits. A higher R2 is always better. Remember to think about which metric best suits your needs and goals. Let's talk about how we make sure our machine learning models actually work well on new data, not just the data they were trained on. We use something called cross-validation. Essentially, we split our dataset into groups, usually around 5 or 10, and then train the model using some of those groups and test it on the remaining ones. We repeat this process multiple times, each time using a different group as the testing set. This helps us spot if our model is just memorizing the training data and not learning general patterns. Stratified k-fold is a variation that's especially important when some of our classes are much rarer than others. It makes sure those rare classes get represented fairly in each test group, preventing skewed results. Okay, let's talk about a really important concept in data science, a bias-variance trade-off. Basically, we want our models to be accurate, but it's a delicate balance. Bias is like how much our model consistently misses the mark. A high bias means it's too simple and doesn't capture the real patterns in the data. Think of it like shooting a target from far away. You're going to miss most of the time. Then there's variance, which is about how sensitive the model is to small changes in the training data. If our model fits the training data to perfectly, including all the random noise and outliers, that's overfitting, and we end up with high variance. It's like drawing a super specific line through your data. It looks great on what you've seen before, but doesn't generalize well to new situations. The goal is to find the sweet spot, a model with low bias and low variance that performs well on both familiar and unseen data. Let's talk about how models can go wrong. The goal of building a data science model is to predict accurately on new and seen data. Sometimes, though, our models get stuck either by being too simplistic or way too complex. Underfitting happens when your model is just too simple. It doesn't capture the true patterns in the data and makes lots of errors. Think of it like drawing a straight line through curved data. It's not going to fit well. On the flip side, overfitting occurs when your model learns too much about the training data, including its noise and outliers. It becomes incredibly good at predicting on the data it's seen before, but struggles with new situations. Imagine a super complicated wiggly line that perfectly matches all the dots in your training set, but makes completely wrong predictions outside of those dots. The good news is there are ways to fix this. Techniques like regularization and cross-validation help us find the right balance, a model that's powerful enough to capture important patterns without memorizing every single detail. Okay, let's talk about feature engineering and selection, a super important step in any data science project. Basically, it's all about taking your raw, messy data and turning it into something that really works well for your machine learning models. Think of it like preparing ingredients. Before you cook, the better your ingredients, the tastier the final dish. We do this by creating new features from existing ones or modifying them to be more useful. There are a bunch of techniques we can use, including scaling numerical data, encoding categories so they're in the right format for the model, and even combining features together. And then, once we've engineered our features, we need to select only the most relevant ones. Too many irrelevant features can actually hurt your model's performance. Okay, so let's talk about dimensionality reduction. Imagine you have a dataset with hundreds of different features. It can be super tricky for your models to make sense of all that information. Dimensionality reduction is like simplifying the data without losing important insights. We use techniques like PCA, t-SNE, and UMAP to do this. PCA identifies the directions in your data that explain the most variation, making things more efficient. t-SNE and UMAP are brilliant for visualizing complex datasets. They help you see how data points relate to each other, even when there are a ton of dimensions involved. Okay, let's talk about time series analysis. Essentially, it's how we look at data that changes over time, like stock prices or weather readings. We break down these datasets into pieces to understand the big picture. Key elements include a general trend showing whether things are generally going up or down, seasonality where patterns repeat regularly, and cyclical behavior, which is longer-term fluctuations. Finally, there's always some random noise that we need to account for. We use techniques like moving averages and exponential smoothing to smooth out the data and identify these underlying components, making it easier to predict what's coming next. Let's dive into forecasting time series data. We'll be looking at three powerful techniques: ARIMA, SARMA, and exponential smoothing. First, it's helpful to understand that we're dealing with data collected over a time, and think sales figures, stock prices, or even weather patterns. ARIMA models are really good at finding linear relationships within the data itself, using past values and errors to predict what's coming next. They're defined by these parameters: AR for autoregression, I for integration, meaning we might need to difference the data to make it stationary, and MA for moving average components. Then we have SARMA's seasonal extension of ARIMA, which helps us account for repeating patterns like yearly trends. And finally, exponential smoothing is another approach that uses weighted averages of past values, giving more importance to recent information, perfect for quickly adapting to changing data. Okay, let's talk about how we really dig into the data, specifically identifying what's going on beneath the surface. We start by looking for seasonality. These are repeating patterns that happen at regular times, like sales booms around holidays or website traffic increases over weekends. Next, we identify trends, the overall direction of the data, whether it's generally heading up, down, or staying steady. Finally, we tackle noise, those random, unpredictable fluctuations that can muddy our understanding. By understanding these three elements, seasonality, trend, and noise, we're much better equipped to build accurate models and extract meaningful insights. Okay, let's talk about stationarity in time series data. Often the data we collect over time, like stock prices or sales figures, isn't constant. It tends to drift and change. That's where the ADF test comes in. The ADF test is a powerful tool for checking if your time series is stationary, meaning its statistical properties remain stable over time. Basically, it helps us determine if we need to transform our data by taking differences before applying certain modeling techniques. It's all about making sure the underlying patterns are consistent. Okay, so let's talk about natural language processing, or NLP. Basically, it's how we teach computers to understand and work with human language the way we speak and write. It's a really important part of being a data scientist because it allows us to unlock insights from massive amounts of text data. We start by breaking down the text into smaller pieces, like individual words or phrases called tokens. Then we might simplify words to their root form, like running, ran, and runs, all becoming run. And finally, we identify what kind of word each one is a noun, a verb, an adjective. NLP lets us do things like figure out whether someone loves or hates a product based on online reviews, or automatically sort emails into categories. It's a powerful tool. Okay, let's talk about prepping text for analysis. Think of it like cleaning up a messy room before you can organize it. We need to get our data in shape first. We start with tokenization, which is simply splitting the text into individual words or phrases. Then we remove common stop words, those words like the and that don't really add much value. Finally, we use lemmatization to bring words back to their root form, so running, ran, and runs all become run. These steps are essential for getting the most out of your text data. Okay, let's talk about how we represent text data for our machine learning models. We start with the basics. Bag of words, it's a straightforward way to count how many times each word appears in a document. It's easy, but it doesn't really understand what those words mean or their relationships. Next up is TF-IDF, which builds on BOW by giving more weight to the important words, helping us focus on what matters most. Finally, we move into the realm of word embeddings, where TOVEC, GloVe, and BOT are all techniques that create numerical representations for words, capturing semantic meaning. Essentially, words with similar meanings will be closer together in this space. BERT is particularly powerful because it considers the context of each word within a sentence. Okay, let's dive into topic modeling using LDA, latent Dirichlet allocation. It's a really cool way to understand what's really being talked about in a bunch of text data. Imagine you have hundreds or even thousands of articles and want to know the key themes they cover. LDA helps with that. It essentially finds hidden topics within those documents, like uncovering the main ideas without having to read every single one yourself. The process involves preparing your text, choosing how many topics you want to find, running the algorithm, which is a bit iterative, and then interpreting those topics based on the words associated with them. Think of it as an automated way to group related documents together based on their shared themes. Okay, let's talk about sentiment analysis. It's a really cool tool for data scientists because it helps us figure out how people feel about things like our products or services. Basically, we feed text into the system, and it tells us if that text is positive, negative, or neutral. We start by cleaning up the text a bit, then look up words in a dictionary that have known sentiment values, and finally, we add up those scores to get an overall picture of how people are feeling. It's used for things like analyzing customer reviews, tracking brand reputation, and even spotting potential problems or frustrations. Okay, let's dive into the basics of deep learning. Essentially, it's a way to train artificial neural networks. Think of them as simplified models of our own brains using lots and lots of data. These networks have multiple layers that allow them to learn incredibly complex patterns that traditional algorithms struggle with. You'll hear terms like neural networks, layers, and activation functions. Don't worry if those sound a little intimidating, but understanding these core concepts is really key for any data scientist wanting to explore deep learning. Okay, let's talk about how neural networks are actually built. Think of them like a really complex series of calculations, kind of like a super smart function. They are organized into layers: an input layer that takes in the raw data, then one or more hidden layers which do all the heavy lifting to extract features and patterns, and finally, an output layer that gives you the answer. We've got some common architectures. Feed-forward networks are simple but useful for basic tasks. Convolutional networks are amazing with images and videos. RNN handles sequences like text. And then there's the transformer architecture, really powerful at tackling complex problems in areas like language. Okay, let's talk about activation functions. They are a really important part of how neural networks actually learn. Think of them as adding a bit of spice to the mix. They introduce nonlinearity, which allows our models to tackle much more complicated data patterns than just straight lines. We have three main ones: ReLU, Sigmoid, and TAN. ReLU is super simple. It just outputs the input if it's positive, otherwise zero. It's fast to calculate and helps prevent a problem called vanishing gradients, which can slow down learning. Then we have Sigmoid, which squashes the output between 0 and 1, making it useful for probabilities. However, it can be computationally expensive and prone to vanishing gradients. Finally, TAN does something similar to Sigmoid but centers its outputs around 0. It generally performs better than Sigmoid in many cases, but also has those same vanishing gradient issues. Ultimately, the best activation function depends on your specific data and what you're trying to achieve, so don't be afraid to experiment. Okay, let's talk about how we actually make our machine learning models learn effectively. It all comes down to optimization algorithms. Think of them as the engine that drives this process. At their heart, they are all trying to find the best settings for our model, minimizing errors and improving performance. First up is stochastic gradient descent, or SGD. This is a pretty straightforward approach. It updates parameters using just one data point at a time. It's fast, especially with huge datasets, but can be a bit noisy and take a while to settle down completely. Then we have ADAM. It's a really popular choice now. ADAM intelligently adapts the learning rate for each individual parameter, making the process much more efficient. And last but not least, RNSprop. This method is also adaptive, using an exponentially decaying average of squared gradients to help with sparse data or problems where things aren't completely consistent. Let's talk about convolutional neural networks, or CNNs. They're a really cool tool for data scientists working with things that have a grid-like structure like images. Think of them as specialized networks designed to automatically find patterns in those grids. Instead of treating each pixel individually, they use convolutional layers, which are like small filters scanning the image and looking for specific features. Then, pooling layers shrink down the information while still preserving important details. Finally, fully connected layers take all that extracted information and make a prediction. Maybe it's an object or a disease. CNN are used everywhere, from recognizing faces in photos to detecting tumors in medical scans. Okay, so we're talking about recurrent neural networks. They're a really important tool for working with data that has an order to it, like sentences or stock prices. The basic RNN can struggle when you have long sequences, but LSTM and GRU are improvements. LSTM introduces gates that help the network remember things over longer distances, almost like having a built-in memory. And GRU is a slightly streamlined version of LSTM, often just as good, but it trains faster. Let's talk about autoencoders. These are a powerful tool in our data scientist toolkit, and they are all about finding hidden patterns within data. Basically, an autoencoder is like a clever compression algorithm built into a neural network. It has two main parts: an encoder that squishes the input down to a smaller, more efficient representation, and a decoder that then tries to rebuild the original from this compressed version. This process helps us reduce the size of our datasets, spot unusual data points known as anomalies, and even extract useful features for other machine learning tasks. Okay, so let's talk about transfer learning. It's a really smart strategy in data science. Basically, we're reusing what existing models have already learned. Instead of building everything from the ground up, which can be super time-consuming and need tons of data, we take a model that's already been trained on a huge dataset, think millions of images or articles. We then adapt it to our specific problem. It's like saying, hey, this model knows how to recognize basic shapes. let me use that knowledge to identify different types of flowers. It speeds things up and works great when you don't have a massive amount of data for your new project. Okay, let's talk about generative models. These models are like digital artists. They learn the patterns in your data and then use that knowledge to create brand new things. We have two main types, GANs and Vs. GAN work with a kind of competitive game where one network tries to fool another into thinking it's seeing real data. Think about creating fake images or sounds. Vs, on the other hand, take a different approach by learning a compressed version of your data like a secret code and then using that code to build back the original data, or even generate brand new stuff from the secret code itself. Both are powerful tools for generating realistic looking content. Okay, let's talk about getting those awesome models you've built actually doing something. Model deployment isn't just about saving a file, it's about making that model available for the world to use. Essentially, it's taking your trained model and putting it into action, like turning it into an actual service. We cover key stages from setting up the production environment where the model lives to creating an API endpoint so other applications can ask it questions, and importantly, how you need to continuously monitor performance and retrain your model as data changes over time. There are different deployment strategies too. Sometimes you'll want to process a whole bunch of information at once, batch prediction, while other times you need immediate responses, real-time prediction. It's all about finding the right fit for your application. Okay, so as data scientists, we often spend a lot of time training models. But what's the point if no one can actually use them? That's where REST API come in. Basically, they let other applications easily access and utilize our predictions. Two popular frameworks for building these are Flask and Fast API. Flask is great for smaller projects. It's simple to learn and get up and running quickly. Fast API takes things a step further with automatic data validation and really fast performance thanks to asynchronous programming. Think of them as the doorways to your models, making them available to a wide range of applications. Okay, so you've built a fantastic machine learning model, congrats. But what happens when you want to use it again later, or share it with a colleague? That's where model serialization comes in. It's basically how we save our models so they don't disappear after the training process is done. We have a few popular options. Pickle is super common in Python, but it can be risky if you're loading files from sources you don't fully trust. Joblib is really great when dealing with lots of numbers and big data sets. It tends to run faster than Pickle in those situations. And then there's ONCS. This is like a universal language for machine learning models, allowing them to work seamlessly across different tools and platforms. Okay, let's talk about deploying your amazing data science models. One really important tool for that is Docker. Think of it like creating a self-contained package for your model, everything it needs to run smoothly, no matter where you put it. It's fantastic because it guarantees that your model behaves the same way in development, testing, and finally production. Docker ensures consistency and portability. You can easily move it between different environments without worrying about dependency conflicts. And if you need to scale up or down, Docker makes that process much simpler. The core of it involves creating a Docker file which basically tells Docker how to build an image containing your model, its libraries, and everything else it needs. You then build the image using Docker build, push it to a registry like Docker Hub, and finally deploy it. It's surprisingly straightforward. Okay, so getting your data science models out into the real world, that's where cloud deployment comes in. Think of it like moving a finished product from your lab to shelves. We've got three big players we want to know about: AWS SageMaker, Azure Machine Learning, and Google Cloud AI Platform, or Vertex AI as they're now known. SageMaker is really great for getting started quickly, offering all the tools you need to build, train, and deploy your models with minimal fuss. Azure Machine Learning integrates super smoothly if you're already using a lot of Microsoft products. And finally, Vertex AI from Google focuses on making things really scalable and automated, perfect for large-scale deployments. Let's talk about how we handle truly massive datasets. First, we have Hadoop. It's like a giant warehouse that breaks your data into pieces and spreads them out across many computers. Then there's Spark MLab, which is essentially a superfast toolbox for machine learning specifically built on top of the power of Spark. Spark really shines because it can do a lot of its work in memory, making it way quicker than older methods at tackling complex problems with huge amounts of data. Okay, let's talk about where data scientists are increasingly turning to: the cloud. Think of AWS, Azure, and Google Cloud as massive data centers that provide all the tools you need to work with huge datasets. AWS has S3 for storing your information, EC2 for running computations, and SageMaker if you want a simplified way to build models. Azure offers similar services, but with Microsoft's approach. And GCP, well, it's known for its strengths in data processing and machine learning. Choosing the right cloud platform really depends on what you're working on, so do your research. Okay, let's talk about the /B testing. It's a really important tool for data scientists when we want to make sure we're actually improving something. Basically, we compare two versions of an element, like a website button or email subject line, to see which one performs better. It starts with clearly defining what you're trying to achieve and then setting up your groups, usually labeled A and B, and randomly assigning users to each group. Then, you collect data and analyze the results statistically. If one version significantly outperforms the other, you know that's the winner. And always remember that statistical significance is super important. Don't just go with what asterisk feels asterisk right. Okay, let's talk about something really important for data scientists: understanding asterisk why asterisk things happen, not just asterisk that asterisk they happen. We often see correlations in our data, things that move together. But correlation doesn't automatically mean one thing causes the other. For example, ice cream sales and crime rates tend to go up at the same time, but eating ice cream isn't making people commit crimes. The real reason is usually something else, like warm weather. Causal inference is all about trying to figure out those underlying causal relationships. It's about identifying the true cause and effect, and it uses concepts like a causal effect, which is what change happens when we do something. We also need to think about interventions actually changing something in our data to see how it impacts other things. And finally, there's this tricky idea of counterfactuals, which basically asks what would have happened if. It's a powerful tool for going beyond simple observations and really understanding the drivers behind your data. Okay, let's talk about something really important: data ethics. As data scientists, we have a huge responsibility because the models we build can actually impact people's lives. It's not enough to just make predictions. We need to think about how asterisk those predictions are made and what consequences they might have. We constantly need to be on the lookout for bias in our data, because if our training data reflects existing inequalities, our models would too. Transparency is key, meaning we need to understand how a model arrives at its decision. You can't just accept answers blindly. Then, of course, there's privacy. We have to protect people's data and follow regulations like GDPR. And finally, accountability: who takes responsibility if something goes wrong? It's about building AI that is fair, equitable, and ultimately beneficial for everyone. Okay, let's talk about something really important in the world of data science: fairness, accountability, and transparency, often shortened to FAT. As AI systems start making more decisions for us, it's crucial that they do so ethically and responsibly. Think about how loan applications or hiring processes are increasingly influenced by algorithms. If the data used to train those algorithms is biased, it can lead to unfair outcomes for certain groups. So, what does this actually mean? Fairness means actively working to prevent discrimination in AI systems, identifying bias and taking steps to correct it. Accountability asks a really tough question: who's responsible when an algorithm makes a mistake or causes harm? And finally, transparency is about making these complex AI systems understandable. We need techniques like explainable AI to peek inside the black box and see how algorithms are arriving at their conclusions. A quote from Alan Turing reminds us that the danger isn't necessarily the intelligence of machines themselves, but how we use them. We'll have links to some great resources if you want to dive deeper. Okay, so let's talk about a really important part of being a data scientist: dealing with bias in our models. It's not enough to just build a model. We need to make sure it's fair and doesn't discriminate against certain groups. Bias can sneak into our models through things like past prejudices reflected in the data, or if our training data isn't representative of everyone. We can spot bias by looking at how well the model performs for different people or some groups consistently getting worse results. There are a few ways we can tackle this, from adding more balanced data to using algorithms specifically designed with fairness in mind. It's an ongoing process and crucial for responsible AI development. Okay, so let's talk about explainable AI or XAI. Think of your amazing machine learning models as powerful but sometimes mysterious black boxes. They give you answers, but they don't always tell you why. That's where XAI comes in. It's all about making these models more transparent and understandable. There are two really popular techniques, SHAP values and LIME. SHAP uses a bit of game theory to figure out how much each feature contributed to a specific prediction, like highlighting the most important factors drive a loan decision. LIME, on the other hand, looks at the model's behavior locally, essentially creating a simplified version around a single prediction to show you what's going on. Ultimately, XAI helps us trust our models more, spot potential biases, and make them even better. Okay, let's talk about recommendation systems. They're basically algorithms that try to guess what you'll enjoy. There are a few main types. Collaborative filtering is like saying, hey, people who like this also like that. It relies on the behavior of other users. Content-based filtering looks at the actual items themselves. If you love action movies with explosions, it'll suggest more action movies. And finally, hybrid systems combine both approaches for a better result. They are often used in real-world applications because they can handle different situations effectively. Okay, let's talk about graph data analysis and how it fits into the broader world of data science. Think about networks like your friends on social media, or even traffic flow in a city. These relationships are incredibly valuable to understand. We'll be looking at the core concepts, nodes, which represent individual items within the network, and edges, which show the connections between them. Then we'll explore ways to identify important nodes who's really influential. How do we group related nodes together to find communities or clusters? And finally, we'll measure different properties of networks to get a better sense of their structure and behavior. It's a surprisingly versatile set of tools with applications all over the place. Let's talk about graph databases. They are a really different way of storing and thinking about data compared to the traditional tables you might be familiar with. Instead of focusing on individual pieces of information, they prioritize asterisk relationships. Asterisk how things are connected to each other. Think about it like this: instead of just listing customers and orders separately, graph databases actually store the connections between them, who bought what from whom. They use languages like Cypher and Gremlin to query these relationships effectively. Neo4j is a popular standalone database with a great community, while AWS NetDyn offers a managed service that's really useful for building large-scale applications on Amazon Web Services. Okay everyone, let's talk about SQL. It's absolutely essential if you want to be a data scientist. Think of it as the language you use to talk to databases and get the information you need. We'll cover some key terms like select from, where, group by, and order by. These are your building blocks. I've included a simple example query here that shows how you can pull specific data from a table based on certain criteria. It's all about getting the right information to start analyzing. Okay, let's talk about taking your data analysis to the next level, specifically advanced analytical queries. We've already looked at describing what's happening and diagnosing why things are happening, but now it's time to really dig deep for insights. There are a few key techniques we'll cover today. Window functions, which allow us to perform calculations within groups of data. CTEs, which help break down complicated queries into more manageable pieces. Subqueries, letting you use the results of one query as part of another. And finally, recursive queries. These can be super helpful for working with hierarchical data. Let's look at an example SQL query that demonstrates how window functions can rank products by their sales figures. Okay, let's talk about two really powerful tools for writing cleaner, faster SQL. window functions and common table expressions, often called CT. Window functions are like super smart calculations that happen across a set of rows at the same time, related to the current row you're looking at. Think of it as doing a calculation while moving along a series of data points. CTEs, on the other hand, are basically temporary named result sets. They're like giving a name to a bit of code that helps break down really complicated queries into smaller, easier to understand parts. They're great for readability and reusability. You can use them again and again within your query. We've shown some simple examples using running totals and rolling averages. Both are much easier to understand with these techniques. Okay, let's talk about how data science actually helps businesses make smarter choices. Basically, companies are collecting huge amounts of information these days: sales figures, customer interactions, marketing results, but it's often sitting there unused. Data scientists are the ones who take that raw data and turn it into something truly valuable. It starts with gathering all the relevant information and making sure it's clean and ready for analysis. Then they explore the data to find patterns and trends. They might build models like predicting what customers will buy or how likely someone is to leave, and finally they share those insights with decision makers so they can actually make better strategic choices. It's all about turning that data into action. And as Bill Gates famously said, data is the new oil. Let's talk about where data scientists are making a huge impact. You see, they're not confined to one specific field. Their skills are incredibly versatile. From healthcare, helping doctors predict patient outcomes and tailor treatments, to finance, protecting against fraud and improving investment strategies, the applications are truly widespread. Retailers use data science for things like personalized recommendations you see online, while manufacturers leverage it for predicting when equipment needs maintenance. Even in entertainment, from suggesting movies you'll love to forecasting what audiences want, data scientists are shaping experiences across a massive spectrum of industries. It's all about using the power of data to drive smart decisions and solve complex challenges. Okay, let's talk about feature stores. As data scientists, we often wrestle with ensuring our models are trained on consistent data and can serve those same features reliably when making predictions. A feature store is like a dedicated database specifically designed for managing these features. It makes it super easy to find the features you need, applies transformations consistently, meaning everything looks the same whether it's being used in training or in your live models, and importantly, delivers those features with speed. Okay, so as data scientists, we deal with lot datasets that can be huge, models that take time to train, and notebooks filled with experiments. Without version control, it's like trying to build a house without blueprints. Git is the core tool here. It's essentially a way to track all the changes you make to your project over time. Think of it as a super-powered undo button. We use commands like add, commit, and push to manage our work. Now, DVC builds on top of Git to specifically handle large data files and model artifacts. Those massive datasets or train models that can be difficult to version with just Git alone. DVC stores these big things in cloud storage and tracks them using Git's metadata system. That way, you can easily roll back to previous versions of your data and models. It's a game changer for reproducibility and teamwork on bigger projects. Okay, let's talk about getting your data science projects off the ground and keeping them moving forward. It's really important to start with crystal clear goals. What exactly are you trying to achieve? Then, we need to do a solid check on the data itself. Is it good quality? Do we have enough of it? And does it actually relate to the problem we're tackling? Don't get caught up in building something huge before you've verified that it's even possible. Agile development, working in short cycles with regular feedback, is a fantastic approach for data science projects, allowing us to adapt as we learn. Keeping your stakeholders informed every step of the way is also key. They need to know what's happening and why. And finally, using version control like Git will save you headaches down the road when things inevitably change. Okay, let's talk about experiment tracking, a critical part of being a data scientist. We inevitably run many experiments as we try to build better models. It can get really messy trying to keep track of what worked and what didn't. Thankfully, tools like MLflow and Weights and Biases come to the rescue. MLflow is a great all-in-one platform that helps you manage your entire machine learning process, from logging experiments to reproducing them and even deploying models. Weights and Biases shines with its powerful visualization capabilities and collaboration features, offering interactive dashboards and easy comparison of different runs. Essentially, they help you understand why things worked or didn't work, making it much easier to iterate and improve your models. Okay everyone, let's talk about keeping our models healthy. Model monitoring and drift detection are key parts of a data scientist's job. Basically, drift means the relationship between what we feed our model and what it predicts is changing. Think of it like the world around your data evolving. We have different kinds of drift, like changes in the actual data itself or even changes in how things relate to each other. There are lots of ways to spot this drift, from simple statistical tests to more advanced algorithms that track performance over time. The important thing is catching drift early allows us to retrain our models and keep them accurate. Okay, so let's talk about keeping our models sharp, not just building them once and leaving them to their own devices. As data scientists, we need to understand that the data world is constantly shifting. Things change, patterns evolve, and what worked yesterday might not work today. That's where continuous learning comes in. It's about recognizing that your model isn't a static entity, it needs regular attention. Specifically, we're focusing on retraining pipelines. These are essentially automated workflows designed to keep our models performing optimally. They start with monitoring data and model performance, and then automatically trigger a retraining process when things need updating. Think of it like a feedback loop, constantly improving your model's accuracy. Let's talk about how data scientists are tackling the challenge of analyzing information as it happens. We're moving away from looking at historical data and diving into what happened yesterday to understanding what's happening right now. This involves using powerful tools like Kafka, Flink, and Spark Streaming to handle those continuous streams of incoming data. It's about techniques like windowing, basically grouping data over specific time periods, and managing stateful processing, which is how the system remembers information as new events come in. Think of fraud detection, spotting suspicious activity immediately instead of waiting for a report. That's where real-time analysis truly shines. Okay, let's talk about getting data from external sources. That's where API come in handy. Think of an API as a waiter at a restaurant. You tell it what you want your request, and it brings you the information you need the response. We send out requests to specific addresses called endpoints, which might require some credentials like an API key for security. The server then sends back data, often in a really handy format like JSON, which we can easily use in our analysis. I'll show you a simple example using Python and the request library to make that happen. Okay, let's talk about simulation and Monte Carlo methods. These techniques come in handy when you're trying to understand systems that aren't perfectly predictable. Simulation is basically building a mathematical model of what you're looking at, like creating a mini version of the real thing where you can run trials over and over again and collect data. Monte Carlo, on the other hand, uses lots of random sampling to get an idea of probabilities or outcomes without needing to solve complicated equations directly. They're particularly useful when analytical solutions are tough to find, such as in financial modeling or figuring out how a disease might spread. Okay, let's talk about advanced statistical modeling. It's where data science gets really interesting, moving beyond simple formulas and exploring more complex ways to understand your data. We're looking at techniques like generalized linear models, which are great for dealing with things that aren't normally distributed, like counts or skewed data. Then there's mixed effects modeling, perfect when you've got data organized in layers, like students within classrooms. Time series analysis is vital if you're tracking something over time, think sales figures or website traffic. And finally, survival analysis helps us understand when things happen, which is super useful in fields like healthcare. I included a little R code snippet as an example of how you might use one of these techniques. Remember, it's not about just knowing the formulas, it's about understanding why and when to apply each method. Let's talk about optimization. Data scientists often need to fine-tune their models for peak performance, and that's where these techniques come in. First up is linear programming, a powerful way to optimize problems with clear constraints and objectives, like deciding how best to allocate resources. Next, we have integer programming, which builds on linear programming by requiring some variables to be whole numbers, perfect for scenarios involving discrete decisions. Finally, genetic algorithms provide a flexible approach inspired by natural selection, especially useful when dealing with complex, non-linear problems or lots of potential solutions. Okay, let's talk about building a really impressive data science portfolio. Think of it as your chance to prove what you can do beyond just saying you know things. It's like showing off your skills with actual projects. Start by tackling some smaller, manageable tasks, cleaning up data or doing some basic analysis. Don't get bogged down trying to make everything perfect right away. The most important thing is to really focus on the results of what you do. What did you actually accomplish? And always try to quantify those achievements whenever possible. Numbers speak louder than words. You'll want to showcase a variety of skills, from working with databases like SQL to using programming languages like Python and creating compelling visualizations. And absolutely use GitHub to host your projects. It shows employers that you understand version control. Finally, remember to keep your portfolio focused. Quality is key. A few strong projects are far better than a bunch of weaker ones. Okay, let's talk about how data science interviews often test you with case studies. These aren't just theoretical exercises, they're designed to see how you actually approach a real-world problem. You might be presented with scenarios like predicting why customers leave a service, forecasting what sales will look like next quarter, or identifying fraudulent transactions, really common challenges businesses face. When tackling these, it's crucial to clearly understand the goal and break down the problem into manageable steps. Think about cleaning your data, creating relevant features that can help you build a model, choosing the right technique for prediction, and then evaluating how well your solution performs. And most importantly, be prepared to explain why you made each choice. Walk the interviewer through your thinking process. Okay, let's talk about how coding is a core part of being a data scientist. We're going to cover the three main languages you'll likely be using: Python, R, and SQL. Python is super versatile. It's great for cleaning up your data, doing calculations, and building predictive models. Then there's R, which is specifically built for statistics and making really nice charts and graphs. Finally, we need to know how to talk to databases with SQL. This lets us pull the exact data we need to get started with our analyses. There are some great online resources like Codecademy and Kaggle that can help you get started practicing these skills. Don't hesitate to explore them. Okay, let's talk about how data scientists actually use their findings. It's not enough just to build amazing models. You need to be able to share what you've discovered in a way that everyone understands. Think of it like this: you could find the single most important insight in your data, but if you can't explain why it matters and how it impacts decisions, it's pretty much worthless. This slide highlights some crucial communication skills, things like translating technical language into plain English, using visuals to make your story clear, and adapting your message to who you're talking to. A good data scientist is a storyteller, not just a coder. Okay, let's talk about documenting your work as a data scientist. It's really important to be clear and organized so others can understand what you did and why. We need to create project documentation outlining everything from the initial goals to potential limitations. Don't forget to add detailed code comments. It's like explaining your thoughts directly in the code. Also, a data dictionary is essential for defining all the variables you're using. And finally, standardized report templates will make sure your reports look professional and consistent across different projects. Thank you for watching.